Hey, chemistry students. Today we're going to learn a little bit about weak acids and bases, and we're going to take a look at how we would do calculations involving them. Okay, so the thing to understand about weak acids and bases is, again, strength or weakness of an acid or base has nothing to do with concentration. Strength or weakness has to do with one thing: whether they completely dissociate in water. That's the key idea here. Completely dissociating in water. So what we need to know or calculate is how much the acid or base has dissociated. Let's do a few examples. A 0.5 molar solution of a weak acid, we'll call it HX, is 1.8% dissociated. Calculate the molar concentration of each species in the solution. So in general then, we can say that this reaction is going to be, let's get our pen rather than our highlighter here. It's going to be HX plus water, which is going to give us the hydronium ion plus OH minus. All right, so what we're going to try and do here is we're going to try and find out what the molar concentration of each species in the solution is. So let's look at the key information in this question. It says that it's a 0.5 molar solution. It also says that it's 1.8% dissociated. So that's key. Okay? So we start off with 0.5 molar acid, and we know that it's 1.8% dissociated. So we need to find out what 1.8% of 0.5 is. So that's going to mean we're going to take 0.018 times 0.5, and that's going to give us 0.009 molar. And as we know, that's going to be what is taken away from the concentration of the acid, but it's also going to be the concentration of the products. So we're going to take 0.5, we're going to subtract 0.009, and we're going to take hydronium and add 0.009. The other species we're also going to go plus 0.009, and then that's going to give us, let's see here, let's go right here. Okay, that's going to give us 0.491 molar for the resulting concentration of the acid, and of course 0.009 molar for both of the products in the chemical equation. So we end up with this much acid left after the dissociation and this much of the products in the dissociation reaction. Okay? So we need to find out what 1.8% of 0.5 was, and then do some subtracting or some adding, understanding that we start off with 0 of this and 0 of this. Okay? All right. Let's try a couple more examples. So a 0.1 molar solution of acetic acid is 1.5% dissociated. Find the hydronium ion concentration and the pH of the solution. Okay, so first things first, we have to write out what the reaction will be. The reaction will be acetic acid, so that's HC2H3O2 with water, and that's going to give us the hydronium ion concentration and the acetate ion. Okay, so again, what we want to do is we want to look at the important information in the question. This is the molarity of the acetic acid. This is the amount of the dissociation. So we want to find out what 1.5% of 0.1 is. So we're going to go ahead and we're going to go 0.015 times 0.1 is going to be 0.0015 molar. That's how much is taken away from the acetic acid. So we start off with 0.1 molar of this, nothing here, nothing here. Then we subtract 0.0015 for the acetic acid, and we add that same concentration to the products in the chemical reaction, which in turn gives us final concentrations of 0.9985 molar and 0.0015 molar and 0.0015 molar. Now in this particular situation, the question does ask us for just the hydronium ion concentration. So that means that the real important information is right here, because that does tell us what the hydronium ion concentration is. But it also asks us for the pH. What is the pH of the solution? So in order to figure out the pH is equal to the negative logarithm of 0.0015. And when you figure that out, what you're going to get is 2.82. So the pH of the solution is 2.82, and we use the hydronium ion concentration of 0.0015 in order to figure that out. And that's all there is to it. So this was a two-step question that asked us for the hydronium ion concentration and the pH, and now we have done both of those things. Okay. All right, and we have another question on this page. And this time we're dealing with a weak base, so we're just going to call it MOH, just some random weak base. It has a molarity of 0.2 molar, and it's 1.2% dissociated, so it asks us to find the hydronium ion concentration and the pH of the solution, okay? So now actually, we're just going to make a wee change here. It's not going to be the hydronium ion concentration that we're going to look for, because we are talking about a base. We're going to look for the hydroxide ion concentration, and we will look for the pH after we find that. Okay? All right, so what is the chemical reaction going to be? Well, the chemical reaction is going to be MOH is going to dissociate to give us M plus OH minus. And we know that we start with 0.2 molar here, nothing here, nothing here. And then we're going to use the dissociated amount, 1.2%, in order to help us go from there. So we see that we have 1.2% dissociation. So we're going to figure out what 1.2% of 0.2 molar is, and we're going to get 0.0024 molar. So if we want to go through and show the concentrations of all the species, we could do that. But it does just ask for the hydroxide ion concentration, and the hydroxide ion concentration is just that. It's just going to be 0.0024 molar. So we don't have to go through all the rigmarole. We could just say it's 0.0024 molar. But now it also asks us for the pH. So to figure out the pH, how are we going to do this? Well, if we could use the exact same approach we did before, where we would take 10 to the negative 14, divide it by the hydroxide ion concentration, and that would give us the hydronium ion concentration. But instead, we're going to try just show you a different method here that might help you, and that is we're going to find the pOH. And to find the pOH, that could be found by taking the negative logarithm of 0.0024, the hydroxide ion concentration. So the pOH, when we do that calculation, is 2.62. Now, once we have that, we can go forward from there. And when we go forward from there, we're going to be using the property that pH plus pOH is equal to 14. We just found the pOH, so that means the pH is going to be 14 minus the pOH, which is 2.62. So the pH is going to be 11.38. That's going to be the pH of the solution. So we just found the pOH, and then we subtracted from 14, and that will give us the pH. And that's how we do that question. And finally, we have a couple questions here. And these questions ask us to actually find the percent dissociation. So it says we have a solution of a 0.2 molar weak acid HX, and it has a pH of 1.65. Find the dissociation percentage. So here's what we know. Okay, here's what we know. That we know that the hydronium ion concentration is going to equal 10 to the exponent minus pH. So that's 10 to the exponent minus 1.65. So if you work that out on your calculator, what you're going to get is 0.022 molar. That's the hydronium ion concentration. So what that means is of the 0.2 molar concentration of the weak acid, 0.022 dissociated of it. So we take the 0.022 that we just found, and we divide it by 0.2 to find how much of that it is. And then to turn it into a percent, we'll multiply by 100. And when we do that, we're going to find that this weak acid is 11% dissociated. Okay? So this weak acid is 11% dissociated. And we have a similar question to that down below. This question now deals with a weak base. So it says a 0.3 molar solution of a weak base MOH has a pH of 11.9. Find its hydroxide ion concentration and its percent dissociation. So if we're looking for hydroxide ion concentration, then we're going to have to find the pOH. The pOH is going to be 14 minus the pH. The pOH is going to be 14 minus 11.9. The pOH is going to be 2.1. So that is the pOH, is 2.1. Then, in order to figure out the hydroxide ion concentration, it's going to be 10 to the exponent negative 2.1 because the hydroxide ion concentration is equal to 10 to the exponent minus POH, just like above, the hydronium ion concentration was 10 to the exponent negative pH. So we take our calculators and we figure out what 10 to the exponent negative 2.1 is, and we get 0.0079 molar. So that will be the hydroxide ion concentration. And then to figure out how much of the original weak base dissociated, what we're going to do is we're going to take 0.0079 divided by the 0.3 molar, multiply it by 100, and when we do that, we're going to get 2.63%. So the weak base has a dissociation of 2.63%. So just to kind of retrace our steps here for this question, we were given the pH, and because we're talking about a base, we're going to want to find the hydroxide ion concentration. So we found the POH by subtracting the pH from 14. Then we used the idea that the hydroxide ion concentration is 10 to the exponent minus POH. And that helped us figure out that the hydroxide ion concentration was 0.0079. And then we took that 0.0079 and we divided it by the original concentration of the weak base, multiplying by 100 to give us that percent, and we got 2.63%. So there are some examples on sample calculations with weak acids and bases. Do the supporting questions and make sure to reach out if you need some help.